Thank you very much. I think what has been presented today has been really fantastic in trying to understand particularly the blood-brain barrier and its different components and how each component interacts with the others in order to maintain the microenvironment of the brain. The blood-nerve barrier is somewhat similar. The big difference, I guess, is that we don't have astrocytes or microglia that provide end feet that contribute to the vascular structure or the neurovascular unit in the peripheral nervous system. So we are still very early stage of trying to figure out how, for example, Schwann cells and the local secretion of soluble factors such as GDNF or VEGF may participate in the development of tight junctions within the peripheral nervous system. I think a very important point that's been brought out from all the conversations here is that there's a very dynamic process that takes place in normal disease, in normal states as well as in disease states, where there's an interaction between cytoskeletal components, adherence junctions, tight junctions, and the cells that support the endothelial cell within the tissue-specific environment, including the matrix, in maintaining a normal function. I guess a big question will be what happens during normal development, and in specific diseases, what perturbations take place that result in the pathology we see.
Okay, so what I would like to add, actually, I would like to congratulate the speakers for a really good and great overview of the field. So I would like to also add that actually things are complicated. And I'm referring mostly to the basal permeability and how that function. Yeah, so we all agree that permeability occurs at the level of capillaries, and you have to have a vessel wall, and the vessel wall is the endothelium forms a barrier. The barrier is maintained by input from pericytes, from the matrix, from the subjacent tissue. Now, for me, permeability is a word, to paraphrase Bill Ayer this morning, he was stressing the importance of terminology. Now, for me, permeability is something that denotes control. So in normal undisturbed tissues, endothelial cells, in cooperation with all the other inputs, exercise this control in which the exchanges maintain homeostasis. What happens in disease or in adaptive processes like in inflammation is the loss of this barrier. So is that permeability? I would really like to throw this out there. I would like to hear some opinions. That to me is leak, is vascular leakage, yes, and that is very, very important. But now, the final point I would like to make is that one, we do not really know how the basal permeability is maintained. Yeah, so we have more than endothelium. We have the basement membrane. We have the glycocalyx that has not been mentioned at all. Now, opinions really differ in the field. You know, by some opinions, the glycocalyx provides the filter, and everything goes through the junctions. On the other extreme is glycocalyx may provide the filter, but there is vesicular trafficking that actually does the job. There are people in the middle as well. So until we do not really understand at molecular level what happens there and how we can actually modify and manipulate these processes in order to answer the question of permeability and its contribution to physiology. And then Bill Ayer also raised another good point, that we see that hyperpermeability in many disease processes, but is it really the driver? Is it just the collateral? I would end here.
I could just add, from the retina, I find it very, first, there are folks in the audience who understand this far better than I do, Jerry Letty, for example, in the back. But if you look at a retina, it's fascinating that in the disease case, the cystoid formation in diabetic retinopathy is not right by the vessels. It is in the outer retina where we just explained there aren't blood vessels. So clearly the process is not just opening and leak of fluid. We often think about Starling's equation, possibly leak of protein and trapping of the protein leading to an osmotic change. But I don't know that any of that's proven, and I'm not sure what folks think in the brain.
If I may just add a little bit to this, there is a new concept that just started emerging, which is very interesting for the field. For example, there is a paper, 2 papers in Nature published 3 months ago about MSF-T2A, which is actually omega-3 fatty acid transporter that also regulates the blood-brain barrier permeability. So there is a direct liaison between nutrient transport, essential transport, and that. We also have work I didn't talk about GLUT1, which is glucose transporter, that is similarly important for maintenance of the blood-brain barrier integrity. I didn't have time. So I think this is kind of an emerging concept. And in terms of how it happens, it's paracellular, transcellular, or misalignment of the time junctions. Anything can be.
Well,
finally, right.
I'm not sure I understand Robert's point. I mean, he's intimating, I think, is that permeability may not be a causative factor in disease. I think that's likely not the case, because permeability means a disruption of the junctions, which enables transport or extravasation of liquid and solutes and plasma proteins, and osmotically, I mean, it's a pathogenic feature in edema formation and all kinds of other things, and inflammatory diseases. Now, one of the things I think we've neglected throughout this afternoon is really to define permeability, because permeability is actually a physical term. It's described in units of centimeters second, and so I think we have to get away from the descriptive aspect of defining permeability and really get down, and that may help to address some of the questions.
Gary showed that in his lecture in MS, right? In vascular cognitive, you did show increase in permeability. They measured that.
Well, but transfer is not permeability. Transfer could be due
Can you use the
to
microphone?
convection.
That's the same as a
But transfer, I think, is a different, because you can have increased. I'll give you an example. You can have increased surface area, and thereby you can have increased flux of large molecules, which could be misconstrued as increased permeability. Increased permeability, I think that. Well,
transfer constant is a PS product. That's it.
but
It's that top.
it is a function of surface area. I don't think you can rule out the surface area.
So can I interject a little, 1 minute here? So we are talking about permeability as a mechanism of a breakdown of a mechanism as in disease. But that's not the only time that the blood-brain barrier is permeabilized. It's also permeabilized as a response to damage and danger signaling. And therefore, it has mechanism to get cells or cellular factors from one place to another, right? And so permeability, so blood-brain barrier permeability isn't just a breakdown of a mechanism during disease. It's also a response, a homeostatic response to damage.
I think one thing we haven't talked about a lot is the role of transporters. I mean, it's a very dynamic process. I mean, I think traditionally we always thought about, okay, this is a large molecule, it shouldn't cross across the vascular barrier, but there is the receptor-mediated, endocytosis. Depending on the tissue you're working in, depending on the state you're working in, there may be very active transport through transcellular mechanisms. And the question is, if I took my high molecular weight dextran and simply saw more of it on the abluminal side, does that necessarily mean that my endothelial barrier is leaky? Or is there an active transport process because of the microenvironment in which my cell existed?
Yeah, I'd like to address that, because over the years, I found out the important thing to look at is exactly what you're saying, but look at different molecular weight dextrans to tell what kind of process are you actually altering in a disease state or a pathological state or an injury state. Is it transcellular? Is it paracellular? What is going on, number one. Number two is, we talked a lot about degradation, we talked a lot about breakdown. What about repair? Repair is a dynamic system. Repair can happen all the time. And the truth of the matter is, we have the caveoli observations, we have the Cavan observations, we have the phosphorylated caveoli observations, and to be truthful with you, they can actually transport the tight junction proteins, and you can have actually a trafficking issue going on, back and forth across a injured, degraded, breakdown blood-brain barrier. You can get trafficked of these tight junction proteins right back up to that point and actually re-anneal that barrier. So it's a dynamic system that takes in all the cell types, but we can't forget the model systems we use, especially this albumin issue with Evans blue. That's a huge molecule, okay? That's like the hole in the dam and everybody's going to get flooded downstream. It doesn't necessarily have to happen that way. It can happen with a small molecular weight molecule that shows you that you have a small leak. That's very dynamic. And to the point, you know, Betsa was bringing up the point about permeability. Permeability is our index. It's our ability to see. You know, Gary's data is elegant in that. The Patlack plots are real. But the bottom line is that, in my opinion, and this is just mine, and I've been doing it most of my career, I guess, and I'm getting old. The bottom line is, what about repair? It's not just a break and then dike. This is something that's been going on evolutionary for years. So the tight junctions are involved, the adherens injections are involved, the parasites are involved, the glia, the microglia, neurons are all signaling, and we have a dynamic system. So please, when you study it, don't think that the whole thing's going to break down, because if it did, like I say, we'd have blood running out our nose and out our ears, and we all go home.
I want to harp on this permeability measurement.
Well, you can harp on it.
Patlack is based on certain assumptions. And I was taught this a long time ago.
Okay.
The true measure of permeability is the reflection coefficient
Right.
of a particular molecule, like albumin, for example.
That's
so,
fine.
So I mean, I think, we need to get our definitions straight. So I want to try to switch a question that bothers me personally, is that, there's this interest in the neurovascular unit, but you know, it's been very hard to reconstitute that unit in a cell culture condition.
Well, sure.
And
You know why?
well, tell me why.
Each cell system's contributing a different factor, and that's why you have
Well,
different
but-
soups all the time, different cells all the time.
That's a cop-out.
It's not a cop-out. You got
No,
five
no.
different cell types all
No,
contributing
no,
something.
but you should be able. You should be
Should?
able to reconstitute it in terms of putting together the
In
different
vitro.
constituents,
Okay.
whether it be astrocytes, astrocyte condition medium,
This is great.
neural factors. So I mean, why?
That's why 20 years ago I moved in vivo, because we found out in vitro it's all black magic.
Okay, I think we can take
That's a
two
good
more
idea.
comments and then, if it's quick, 3.
I just have a question is when you actually disrupt these cell matrix interactions like Greg just showed, Greg is talking. You know, when you disrupt the interactions, the cell matrix interactions, because you change the types of integrins that are expressed. Just going back to what Bill Ayer had shown in his talk, that you may actually change the transcriptional profile of that endothelium, because now that integrin is engaging a different kind of extracellular matrix protein. And have you looked at anything to see that whether there's any transcriptional downstream effects?
Yeah, that's the
there
point of
in
the
your
current,
schema?
current work, which I didn't describe, and it's a little too early days to say what happens downstream from that. I mean, we believe that the endothelial cell cultures, particularly on inserts, are at a steady state, but they're probably not. And so, I mean, truth in advertising is that although the viability of the cells is 98%, even in conditions of oxygen glucose deprivation, there may be some component of proliferation, which changes the dynamic anyway in terms of transcriptional factors that are involved, and also adherence, integrity, I guess I would say. So we expect some change. And if one's looking at signaling events, it really does depend, as you probably well know, on when you've when you've begun the culture, particularly for primary and P2, P3 cells. I mean, we've avoided all of the long-term generated cell lines that are immortalized because we want to look at signaling. But there's an acute dynamic, and then there's a more steady state dynamic. And which one is true? And so that's a part of the problem we're dealing with right now.
Well, I was thinking more actually looking in vivo, if you could do some microdissection and take, after ischemia, take those endothelial cells and do some profiling.
No, we haven't done this. It'd be marvelous to do. You know, I make a plug for non-human primate studies. The era of non-human primate studies for this work, I think, may be gone. And this would be a horrible thing, because this is a phenomenal model. From the standpoint of ischemic stroke, it is probably the best model on the planet outside of the patient, which we don't have access to material to. I've been able to maintain for about 20 years materials in freezer at minus 80 degrees, but they're going to deteriorate over time. So we could look at this question, but it won't be a complete answer. A few years ago with the Genomics Institute of Novartis, we looked at some of the material from an RNA standpoint, and it's really, really interesting stuff. And we have to do the single cell studies in order to be able to understand what's going on. I hope we can come back to that. I would hope that some group like the NIH would like to have on campus a primate facility run at a very high level to which investigators like those of us in this room could go to and do these kinds of experiments in a controlled way, and the materials would be available to everybody. That would be phenomenal. That's what we're missing.
One more or two, if it's very brief, please, brief questions, brief answers.
Yes.
I don't know if this is the
Gentleman
right
over there.
venue, but no one's talked about when the cells are really permeable, that is when you have a microhemorrhage. So could someone talk about capillaries that are leaking out red blood cells or arterioles that are leaking out red blood cells?
Yeah, so Gerhard Hamann also in our group looked at the correlation, this is a correlation between the breakdown of matrix in the capillaries and larger microvessels up to 100 microns, and the development of microvascular hemorrhage or minor hemorrhage. And there's a very strong correlation. So, the basal lamina, while it's dynamic in its own way, is also a pretty good force, a good nice fence to prevent cell transit. Yeah. So that's very real.
So the chemical engineers that talk about a 3-pore model, a pore through a closed junction, and that might be regulation of ion flux, pores through broken junction. And I think a lot of what we've talked about with dye markers like dextrans or albumins are following that. And then large pores, dead cells. I mean, and these pathological processes probably include all of those steps. And sometimes, I think Dr. Malik is absolutely right. We need to be maybe very careful about defining permeability, because we may be looking at different parts of an ongoing process, and that may very well be a longer stage with endothelial degeneration and death, leading to very frank hemorrhaging.
Yeah, in fact, that's true. I mean, recent observations, some from us and some from Dietmar Westweber, have shown that different signaling events mediate permeability, truly measured permeability. A different phosphorylation of weak adherent mediates permeability of albumin, let's say, whereas phosphorylation of weak adherent at other site mediates migration of leukocytes or red blood cells. So it isn't, I think it's simplistic to say if you have permeability increase, that's going to transport proteins as well as formed elements. That's not the case. There are discrete pathways mediating each process.
Dr. Davis has a comment? No? Can I just make a very brief comment about microvascular lesions or microhemorrhages, because it's seen in many diseases like Alzheimer's or ALS and etc. There is a recent work in PNAS by graduate student Ethan Winkler, who is now neurosurgery resident. When you increase microlesions pharmacologically with warfarin in ALS model, you can influence neurological course of disease. And other way around. If you reduce the numbers by closing the barrier, you can control the motor neuron disorders. So I think that's one of the examples how the capillary originated. These are microhemorrhages, 50 micrometer capillary originated can influence the course of neurological disorder. I think it's a nice,
Right.
he did a nice work. Making you were on his committee, right?
You know, I love animal models. I mean, they're the best thing to anything. But the sense of the discussion, there's an anti-cell culture aspect of the discussion. Well, I think that cell culture experiments are not a charade. You know, they have meaning, and they're if you address the question properly, or if you address a particularly interesting question, then they're obviously a valid tool. Someone mentioned they're getting out of cell culture experiments doing animal models. Well, I think you should get back into cell culture and really try to address questions at a very basic mechanistic level, because animal models, although wonderful, the best things since sliced bread, I mean, have limitations also. And I think that having appropriately controlled endothelial monolayers is a wonderful way to go. And that's what bothers me, that no one has been able to constitute a blood-brain barrier. Because if you could reconstitute it, then you would understand the makeup of the barrier. Because, you know, I mean, your studies are not telling us what the makeup is.
Yeah, I just wanted to make a comment about that, because if you take an endothelial cell from the brain, you won't get the electrical resistance. It'll always be too low.
Why?
Well, because it doesn't make a tight junction. And then if you add an astrocyte, you will bring up the electrical resistance, and it'll look more like an actual cerebral capillary. We're now putting back in pericytes. And pericytes are absolutely critical. Each one of these cells makes a different component of the tight junction. And when they break down, you see the tight junction proteins in different cells. So I think the complexity is we're getting close to being able to imitate it. I don't know if we'll ever get the true electrical resistance that Krona was able to get in his capillaries. I think it's 80 something, but it'll be closer. And you just have to have somehow each of these cell types makes a different aspect of the tight junction protein. And if you don't make the tight junction protein, you don't have the blood-brain barrier. So I don't think it's hopeless, but it's very complicated.
But also you have to incorporate flow. There's evidence that flow makes a big difference in the formation of tight junctions as well.
That's exactly right. And I don't want to leave anybody thinking that in vitro is a bad thing. You complement your in vivo with your in vitro, and you've got the full caveat. But you can't forget flow either, and the tortuosity factors that also affect the endothelial cell tight junctions. So it's a very complicated issue. Yes, you need in vitro for mechanistic studies, but by God, stay as close to in vivo as you can because of the specialized nature of all these cell types, as Gary just pointed out. Thank you.
Okay.
So I would also like to point out that what some of us are not talking about is the quality of the endothelial cells that we're using, whether they are cell lines or primary cells. That makes a huge difference. And also from work from my observation from work from our lab, apparently what astrocytes produce in culture is even better than using the astrocytes themselves, because we get higher transendothelial resistance if we use the supernatant from cultured primary astrocytes, and much better than we get when we use the astrocytes themselves. So obviously there is some component with that astrocytes produce, and that's tightening, resulting in a tighter barrier. So there are a lot of things to explore here. But what I do know is that some cell lines you use cannot recapitulate effectively what you would observe in primary cells.
Okay, very quick, please.
Okay, getting back to this idea that do endothelial cells in vitro lose their characteristics when the endothelial cells in vivo, when they're put in vitro, do they lose their characteristics? Do they retain some, as Blair said, or lose others? Okay, so if you compare UVEC from umbilical vein to HEDMEC or to HEPMEC from pulmonary microvasculature, you see distinctions that are retained in vitro, and if you measure, as Asser said, by electrical resistance, there's a big difference. And as far as Dr. Rosenberg said, the tight junctions are retained in the HEDMEC, and if you knock down Claudin 5, for example, you lose that barrier advantage.
Can I make a quick comment about cell culture preparations? Because in the last couple of years, there have been several groups that are starting to work with iPS cells. They're working with human cells. And Eric Schuster's group in Wisconsin has been able to put together a brain capillary endothelial cell model, right, from iPS cells that has a transient endothelial electrical resistance that is pushing 3,000 to 4,000 ohm centimeters squared. Okay, and it has many of the molecular characteristics that you would expect to see in a blood-brain barrier model. So there's a new dimension to this area. I'm not a great believer in cell culture. I'm probably from the Tom Davis school, but I think this has tremendous potential because you can get cells from people. You can get cells from people with various diseases, and you could make the endothelial cells and see whether or not you get the same characteristics for transport, for electrical resistance that you see in controlled cells from control patients.
Actually, you can buy them. There are places that sell primary brain, human brain endothelial cells. Yeah, we don't get them from undergrads.
Okay, I would like to thank all session 4 participants, speakers, chairs, and discussants. And I would like to invite my co-chair, Dr. Zorina Galis, for some concluding remarks. And I'll just start. In addition to Dr. Ramadan and Husman that Dr. Storylandis acknowledged this morning, it took a village to plan this workshop, and there are a few other colleagues that I would like to thank, Dr. Jim Koenig and Dr. Rod Corriveau. Rod is not here, unfortunately, but they were tremendous in this planning effort, and it was really a teamwork. And Zorina will thank her staff in Heart and Lung. Just some remarks from the NINDS perspectives. I think we considered this first day a success based on the lively discussion that we got, and that was exactly what we expected to see. And I thank you all for staying up until this time and for participating so actively in the discussion. I think we covered a lot for the first day. I think some of I can't possibly recapitulate all of the topics, or we would stay here until midnight, but some of the major topics that emerged is the importance of sex differences in the vasculature, the complexity and heterogeneity of the microvasculature, as well as the influence of both genetic and environmental factor. I think there was a lot of discussion on cellular interactions, and particularly the interaction between the microvasculature and the immune cells. Some discussion that in the late session about the unique features of the blood-brain barrier and whether it could be modeled in vitro, and it looks like this is still a topic of debate. Some other concepts that emerged is whether small vessel disease is a unique disease, or if it's just a continuum of vascular pathology and the large vessel pathology. And also the topic of repair. I think what also remains to be discussed is the chicken or the egg issue. Is small vessel pathology causing the disease, or is rather a disease process that is affecting the small blood vessels? And I think we may be hearing more about this tomorrow. And with this, I'll just leave the microphone to Zorina for her remarks. Thank you so much. And also after this, if you think there are topics that were not covered today, but you would like to discuss or mention briefly, we would welcome any additional input from the attendees. Thank you.
So I also want to thank everybody. It's very exciting to see so many people coming from various areas of research. NHLBI is covering a lot of territory in terms of vascular structures in various organs, but when it comes to disease, to the disease state, usually people migrate towards the specialized institutes. So we find that many times we get lost in translation, going from knowing the basic biology or the physiology to the specific changes in the organs. So in order to put this together, it took more than 2 institutes. Actually, it took several institutes. We started a small blood vessel group within the NIH. I would like to thank the whole group, which is too long to call out. I could call out a couple of people who are closer to we're closer to the organization of this meeting, and that was Christine, Marek Belkin, Mark Charette, and Esther Tolunay. They all work at NHLBI, but we requested recommendations from all the institutes. We actually had to lobby and show them that there is this research going on across the institutes, and many of you are recipients of awards from various institutes. So I feel, I don't know if I'm a fan of Malcolm Gladwell. In one of his books describes the best place where innovation happens is a bar on an island. Some of you nod their head, they know, where all the ships come from all over the world. They have to refuel and change cargo, and everybody gets into the bar and they all discuss what they learn in China or Africa or wherever they are coming from, and there is this huge information exchange. So I feel like we are like that. Later you can even reproduce the exact bar scene. Right now it's just the interaction of ideas. It's nice to see that some things didn't change much. I have to say that I didn't follow very closely the permeability issue. I see that's not changed so much. I remember my very first manuscript was rejected with one line saying caveolae do not exist. So that was it. There was no way we can prove that. Now caveolin is doing everything and caveolae are everywhere and so forth, but we're still wondering what permeability is. So I agree we have to, probably what this group can do very well is to agree on certain definitions. By the way, for the purpose of our small blood vessel group, we decided that small blood vessels are arterial, capillaries, and venules, anything that's not a large artery, so don't think only microvascular. Think probably even a little bit bigger. So I think definitions are going to be very important, and they're going to be one thing that we could all probably work on. The other thing that I think would be very nice to do is to, in the end, maybe discuss how systemic diseases affect the endothelium. Looks a little bit different, but more or less is continuous throughout our body if the models were right. So it's one big vessel in the end, and how various diseases affect us, and how we could potentially learn from differences in organ presentation. Another example that I thought was very nice was the discovery of these nets. George Palade showed these bodies, the variable Palade bodies, and nobody knew what they were doing. It's been 40 years, 50 years, I don't know, but finally we see something that seems to be very relevant. So hopefully we can accelerate the process by talking to each other. I think it's going to be interesting to continue the conversation about what's the effect of using in vitro models versus in vivo models, deconstructing versus maybe splitters versus lumpers, right? So the splitters would be people who take the system and deconstruct it to the simplest units, and the lumpers are using the animals and hope to understand everything that's happening. So I think there are certain themes that will go across. I don't want to repeat the topics. We wanted to give a chance to the audience to bring up some topics that we didn't discuss, but please do not give a lecture. Just throw an idea there and see what comes back. Okay? Thank you.
So I know it's late, and I'll try to be brief, but I want to caution you from considering the endothelium throughout every organ the same.
I
consider
did not
it very
say
different.
that.
Okay.
I said that we have an endothelium that covers all
Okay.
the blood vessels. So
I think of a disease like preeclampsia, and I don't mean to keep harping on this, but when I think of preeclampsia and the manifestation that is so heterogeneous in so many different women, I think of it as the weakest link. So when you start having placental disease, you start having brain disease, you start having liver disease, to me it's the weakest link that's getting hit, and you're starting to have end organ damage. And that's when I think pregnancy is almost a stress test to these different organs. But it's the endothelium, the heterogeneity in those organs, that's actually getting affected. So I think of the endothelium as being actually very different in every organ, and it's going to be very disease-specific about how it's getting hit. So sorry if I misinterpreted what you said, but I just think we need to think about it.
I actually did graduate work showing the difference in transport, even different molecules are transported in different ways. Capillaries work differently than arterial. I would never say that, but we do have an endothelium that is probably, and that was a question that I have for all of you, how does the differentiation occur? Is it in response to the environment flow, interaction with other cells? When do you form the tight junctions in the brain? What's the role? Is this immunoprotection or whatever it is? And I don't know anybody addressed that. When do you actually get that specialized features? Go ahead.
So we haven't heard very much about vessel dynamics, and especially for the vessel dynamics, right? So these blood vessels serve this purpose to actually tune the blood flow to the organs that they serve, and they tune it according to metabolic need, or to a certain extent. Actually, we have really no idea, right? We study this in the brain, and this is the basis of the signal that you measure in functional MRI. There's actually localized hyperemia when neurons are firing. And we haven't really heard anything about that today. We haven't talked too much about neurovascular coupling and how the blood vessels actually dilate in response. But one of the other things that's really important is that that dynamic tuning of the blood flow is important for the health of the tissue. And so when we've been talking about vascular dysfunction and physical problems with the vessels, everybody said, oh, it must be blood-brain barrier leakage. It must be some problem with the sort of structure of the vessel. But if that vessel is no longer functionally responding, its dynamics are no longer normal, it's sluggish or delayed or doesn't reach a threshold to do what it needs to do, you could imagine that would lead to dysfunction of the organ, death of neurons, even sort of acute performance failure by not getting the nutrients that it needs. So it's another, and we haven't really talked about things like endothelial signaling, vasodilation, vasoconstriction, and all of the signaling pathways that are involved in that. And that, we think, could be a major aspect of brain health and another link between the systemic dysfunction and the brain problems.
Thank you. We have more comments.
I was a little disappointed in the way the program had so little to do with the microcirculation in the heart, because clearly non-occlusive ischemic disease in women, and what used to be called Syndrome X or whatever, and NIH did support the WISE study, is a major health event. And we really haven't really addressed that except for maybe one talk in terms of the microvasculature in the heart. So I think that's an area that needs to be improved and really pay attention to the sex difference. The second comment in terms of cell culture and the difficulty in constructing some of these. I would just, I mean, I hate to be the sex patrol here, but, you know, pay attention to what sex these cells are coming from. Not all HUVECs are one sex. And if you're combining cells from the, you know, the capillaries and the astrocytes and the neurons, are they the same sex? Are you mixing sexes? Does it matter? And the third thing that affects that is what's in the culture media in terms of the hormones that are going to affect those cell cultures. I know for the smooth muscle cells and the endothelial cells that we do when we were looking at steroid activity, we would typically strip the serum of charcoal to get rid of the hormones that are in the fetal calf serum or whatever. I know nothing about what kind of media you use for capillaries or brain cells or astrocytes or parasites or anything like that. But pay attention to that, because if those hormones are there, they're going to have a very different effect depending upon what receptors are being regulated or expressed in the tissue the cells that you're trying to culture. Just two cautions that are so obvious, but we always forget it.
Dr. Miller, we actually have a workshop that's looking at that specific sex differences, sex bias in research, and how the applicants may or may not choose to look at both sexes when they do their experiments. But I do have a challenge for you, and I've been always intrigued by the fact that even male cells have a female mitochondria, right? Mitochondria come only from...
Yeah. That's true. I'm not making the point that you have to study both males and females, okay, in your cell culture. I'm making a point that you have to know what you are studying and actually report it.
That's exactly what I said.
Yeah,
they don't report the two genders. They don't plan on doing it, or they don't report it, or they don't pay attention. That's what we call bias.
Okay, so let's not confuse having to do both cell types with the idea of knowing what you're studying. And I think that's a huge misconception within the scientific community in terms of what we're talking about in terms of sex bias. So thank you.
So mine is not a complaint. It's just a suggestion for the discussions maybe tomorrow, and it's the role of developmental processes. As you know, many developmental processes, either in the vasculature or in any territory, get replicated in part or in total during disease. So it would be interesting to think during the discussions that will come up in the next day, to think about the role of progenitors. I mean, we now know many of the progenitors of the vasculature, how do they fade during normal development as well as disease. For instance, you know, the role of the perivascular progenitors, how much they contribute to fibrosis, et cetera, et cetera. So just as a plug, just to keep remembering that, if we think also of building eventually a kidney or what have you, I mentioned that at the beginning today, we need to keep that in mind. And that, I think understanding these kind of processes, developmental processes, may help us harness the biology a little better.
Mas after from Yale. I'm an emergency physician, so
Thank you for coming.
I've actually learned a lot from all the basic science work today. My question really comes from clinical observations that we see a lot of patients with chest pain. The focus of today's talk has been more about thrombi and ischemia. I see patients and we're screening them before they've had their heart attack. And we find a high prevalence of microvascular dysfunction as opposed to microthrombi. So I guess it goes back to the question about vascular hemodynamics, whether that should also be studied, because these patients are coming in with symptoms which are exactly the same as angina or heart attack, except they have they don't have troponins or evidence of end organ damage. The other interesting observation is in these patients, they tend to be young. There does seem to be some systemic process, like a lot of them have either migraine or metabolic syndrome or lupus or some other form of inflammation. And so I think it goes back to that question whether we should be studying it as a systemic disease with specification to individual organs or not.
Following what Ariel Gomez said before, we heard today about angiogenesis many times, but we haven't heard the word vasculogenesis. And all the small vessels, capillaries, arterioles, venules, develop by vasculogenesis. So I think we need to go back and discuss development.
Something worth focusing on?
Now that we are just between friends, I can tell you that we had all those speakers invited, but we were not as interesting as 2 meetings in Europe in the same time on angiogenesis development and vasculogenesis. And we also had the coronary specialist invited, but he had the wedding he needed to attend. It's really very hard to put a program like this. So I suggest that you may want to make a note. You should have done this. You should just say, can we talk about this? Chances are within 300 people who are here, somebody can address the topic. That was our hope. And I was hoping that you will get an answer. I don't know if you want to have a dialogue, if somebody has an answer, please, I applaud an emergency room physician.
So one thing that I think would be worth talking about that we haven't talked about much today is the cells inside the vessels and the interrelationship between the spatial aspects of those cells and the vessels themselves. So for example, every single blood cell's too big for capillaries, right? They're all bigger than capillaries and they have to squeeze through. So the difference in blood flow that you get when you've got red blood cells flowing through a capillary versus a white cell that comes in is going to have differences, presumably, in oxygenation of the tissue, and then transporting that white blood cell across some adherence across the cell blood wall. That's going to block flow for a while that actually gets moved. So all this kind of stuff is going to play a role that we haven't really talked about today, and I haven't seen much in the literature talked about either, and it would be worth looking at because it may be that there's some problems going on with the way that the cells stick to the vessel walls themselves.
I'd like to interrupt. If you had an answer, maybe
microphone. Yeah,
this could be a dialogue. You don't only have to ask questions. You don't only have to ask questions. You can give answers also.
See a lot of patients who have a systemic problem and then they go into a confusional state, delirium, that sort of thing. And I think if you look carefully, you'd probably find cytokines would be the link between what's going on in one organ and what turns on the damage in another organ. But then it's also age. So if you have a vessel that is not as functional as it should be, and it's exposed to an abnormal cytokine, and TNF, IL-16, those kinds, it becomes dysfunctional for a period of time. And then, of course, it's not structural, so it can go back and we see this a lot in, like an MS patient gets an infection, they come in with an MS attack. So we definitely have to think about how one organ is influencing the other. I think that's a very good point.
So I would like to follow up on that. I have to say this was a feast today.
Introduce yourself, please.
I'm Connie Ryan from Stanford. My primary interest actually lies in inflammatory blood vessel disease, the vasculitides, and the autoimmune diseases. And I have to say, from our point of view, almost every chronic inflammatory disease is complicated by what we now call acceleration of cardiovascular disease. To be honest, we have no idea how that happens. We can only speculate how that happens. But what we do know is that the phenomenon has two major characteristics. First of all, The aging process is centrally involved. And of course, one can come from the side of the blood vessel and say, oh, the blood vessel is age dependent. But the inflammatory system is equally age dependent. Nothing changes as dramatically as we go through life as our immune system does. And an old immune system, unfortunately, does not only become less effective in protecting us, it becomes much more aggressive in being inflammatory. So we have a combination of an aging blood vessel with an aging immune system. And I think that makes our patients susceptible to what we call acceleration. I think it goes beyond soluble mediators and cytokines. It's probably very, very critical which cells are there and how our immune system is regulated in terms of protective and non-protective immune responses. And the other phenomenon what we have is this really strict territorial behavior of these inflammatory vascular diseases. I mean, how these diseases know exactly where to go is absolutely fascinating. But we use it clinically every day to make a diagnosis. So there must be something that tells the disease where to go. So if the vascular biologist could help us to understand that, that would be very cool.
So just a quick comment. Just so you both know, she's talking about very young patients, 30s, 40s, not older patients.
Right. Yeah, that's where we're diagnosing. Otherwise, they have regional defects and they have clear coronary artery disease. So the symptomatic patients that at least we're finding are, at 30, 40, 50-year-olds. So they're young. So aging doesn't necessarily make sense completely, but the vasculitis seems to have some connection, like, they have MS or they have lupus or something else.
So I was going to bring that.
Yeah, why don't you go ahead?
Actually, this penetrates all through the patient cohorts. If you go into patients that have rheumatoid arthritis, their acceleration is by about 10 years. They get their cardiovascular disease about 10 years earlier. And they can't recover as well if they have an injury. It's actually the rare patient that has true vasculitis in the setting of the connective tissue diseases. These are the patients that have vasculitis and they have a primary vasculitis, but secondary vasculitides are not that frequent. What bothers us clinically is the fact that patients that would normally have their disease at the age of 75 now have it at the age of 60. And I think it's acceleration during the second half of life that happens.
I think there's some also, as I also agree, I don't know, I mean, I'm sure age has a big effect, but at least in autoimmune diseases like lupus, where you have a 50-fold increase in the incidence of atherosclerosis, and these are women between 35 and 40 years old, there is something fundamentally about the inflammatory response in the glomerulus, in the kidneys, or wherever the lupus hits, that really increase, and it's not very well studied and not really known, and I think that's some of the gaps in knowledge that we need to fill.
So I wanted to, I got in line when they were talking about the sex differences, and I wanted to push back on a couple of points that have been made. First off, on the sex differences, the idea that we need to know what the sex of the cells are in our culture, I don't think is warranted. I think it's ridiculous, because I put it out there. I want somebody to tell me what, the Y chromosome has very few genes on it. Those genes are not being expressed in culture and endothelium. I want to know of an example. Certainly there are sex differences in vascular diseases. That's no question about it. But the idea that male endothelial cells and female endothelial cells in culture are going to behave differently, I'd like to hear an example of somebody who's seen that, because I've not seen that. So, I'm going to start, we're going to start saying we have astrocytes from men and the rest of them.
In the body, where they are
Obviously,
baited by
in the body,
hormones and other things.
Where there's endocrine effects, there's no question there's sex-related difference in vascular, but the idea that in culture we now need to think about whether or not the astrocytes or the endothelial cells we're looking at are coming from men or women, it's imaginary. And the other concept that's come up is that idea that we think endothelium's all the same throughout the body, and we've got to keep that in our mind. Nobody thinks that endothelium's the same throughout the body. I mean, it's obviously, even in the eye, we've got, within a millimeter, the retinal vessels are completely different from the choroidal vessels on one side of the retina and the other side of the retina. So the retinal vessels have vascular tone, choroidal vessels don't have vascular tone, the retinal vessels have a barrier, the choroidal vessels are permeable. There's no question that there's the tremendous heterogeneity of endothelium throughout the body, the glomerulus. So, you know, just, I think that there's some just like a misconceptions that we're not considering, you know, we have to consider sex when we don't consider sex, or the endothelium is variable and we haven't considered that. That's, you know, part and parcel of vascular biology. I think everybody here understands that.
If I can make a brief comment, I was going to get to it tomorrow session, but because of the discussion of inflammation and how aging is the definite factor and everything gets worse, you know, autoimmunity and inflammation, and this is the maybe a U-curve that exists, and this is something that I want to bring up to this community because I study neonatal and childhood stroke and experimental models that we developed, and the statistics is very staggering for childhood stroke that oftentimes within the 6 months after chickenpox, or after, you know, different infection, it may be viral, it may be bacterial infection, the stroke hits, and it hits mostly the boys, not the girls. It's 1 to 6 approximately, you know, girls to boys, and you know, this inflammatory component, it does present, and it's very profound, and vasculature is the one which suffers the most, because these arteriopathies that several grants P50 mechanism study now that show that vasculature is the one where all these processes begin, and then they just it leads to childhood stroke, to you know, repetitive strokes actually in children. So, and I don't know how many of you know that neonatal stroke is as frequent as it is in adult population, in elderly population, and inflammatory mechanisms are clearly present there too. So that is why we should not, I think, you know, discard the fact that immaturity is also very make the brain and other organs, you know, the blood and leukocyte component is very, very profound, but in different ways than in adults. You know, it does happen. So we need to discuss it. That is why I very much appreciate the comments that say we need to look at what happens with development. Maybe it's a topic for a different workshop. You know, it's impossible to cover everything. It's just too rich for soup for all individual topics. But I thought it's important to bring to your attention.
I can't let that comment go.
We knew it.
Okay. Let's just say that I think there is a lack of evidence right now as to what is different and what is not. And I think that gap has to be filled. There may be many things within a cell that are not that are the same between males and females cells, but do we know what those are? If you look at what's on the X chromosome, there might not be many genes on the Y chromosome, but hello, one of them regulates norepinephrine development, and there's some also that be macrophage adhesion, and there are a lot of genes on the X chromosome that affect diseases, including some cancer, especially to melanoma, to mitochondrial function, and the fact that you only have one in a male cell and you have two in a female cell, some of those genes are activated, some of them are not. I was talking to somebody before, there was a difference in response to hypoxia. Just because we don't have the evidence doesn't mean that there's not a difference there. We need to be able, we're scientists for heaven's sake, we have to be able to understand the variables that we work with. I don't think it's too much to ask somebody to report what the sex of the material is that they're investigating. How can somebody else down the street reproduce your experiment if that data are not in your paper, for heaven's sake? We used to be able to report sex, age, diet, light cycle, and all this other stuff back in the day when I was a graduate student, and I'm sure that was 40 years ago. But what happened? The methods got put into the supplemental material, we cut it down because of impact factor, and now nobody can reproduce anybody else's experiment. Okay? I mean, we need to be able to do this. And what's fundamental about scientists, we want precision on this and precision on that, and taking your equipment down to a certain level to measure some, just report the sex of the material that you use. If there's no difference, great, let us know. If there is a difference, great, let us know and move forward.
And I would also say that, you know, to stand here and say, you know, don't tell me that there's heterogeneity because it's so obvious to me, is dangerous. I think we've been working, many of us in this room for years to try to teach the vascular biology community, let alone the non-vascular biology community, that not all endothelial cells are alike. And you know, the problem with the glut of literature right now is that we take endothelial cells in culture and we extrapolate to every vascular bed in the body. So, you know, I think from the standpoint of the comment that was made about, you know, well, of course there's heterogeneity. I think, you know, that's Monday morning quarterbacking, and I think we've got to be really careful to, you know, before we just say, you know, don't tell me what's obvious, because I think it's been a huge limitation in the field. So.
Thank you very much. I think we'll stop here.